What's up guys, Dylan here and welcome to Advent of Code Day 7, 2025 in Python. If you like this video and find the explanation helpful, please leave a like and a comment down below. And remember that if you want to see the code for yourself, you can check it out in the GitHub link in the description. So without further ado, let's go ahead and get started. So after taking a look at this problem here, it looks like we teleported into an unfamiliar room, and to recalibrate the teleporter, we kind of have to do some calculations with what it calls the tachyon manifold. And basically, it just says that a tachyon beam gets shot out from this S position, and any time it hits one of these carets, it splits. So for this first problem, it just looks like we need to calculate how many times that the beam splits. Now, at first glance, I was thinking that we could perhaps just count the number of splitters that there were, but if you count this up, there's actually 22 splitters here, and it only splits 21 times. So why is that? Well, for example, on this one right here, the beam never reaches the splitter, so that approach won't work. So I think we're just going to go ahead and simulate all the beams traveling down and count it up as we go. So taking a look at the code here, we'll go ahead and start in our parse function. And if we take a look at our data here, each line is a string. But we want to go ahead and convert each line to a list, where each item in the list is just a character from the string. And that way we'll be able to edit the data as we go. So we'll just go ahead and say data is equal to a list of lists. And for the second list, we'll say L for L in line, for line in data. And I'm actually going to go ahead and insert the very first beam on the second line here. So I'll just say, let's see, insert the initial beam, and for, let's say for column and range, length of data, well, they're all the same, so arbitrarily 0. If data in line 0 in column is equal to capital S, then data in the next row of the same column will equal to the vertical bar, the beam. And then we can just go ahead and return data. So giving this a test here, data is equal to parse data. And if we go ahead and print this out, you can see that it's exactly what we expect here with our first beam inserted. So now getting rid of this print and getting started, we will simulate the splits. And we're going to return the number of splits. So we'll go ahead and make a variable for that. And we will start looking from row equals 1. This row right here, which is where the beam is at. So while row is less than the length of data minus 1, and the reason why we do minus 1 is because we'll always be checking whatever row we're in, we'll be checking a row ahead for the splitter. So we want to make sure that we don't hit the end of the list. And the first thing that we're going to do is we have to search for the beam, or any beams. We're just going to find all the beams in the row and then either split them or not. So for column in range, length, data, row, then if this square, if data, row, column is a beam, then we want to check below it. So we're either going to split or not. So in the split case, if data row plus 1, so if the space below it in the next square in the same column is equal to the splitter, then we'll increase the number of splits by 1, and then we'll insert the beams in the next row. So for data in the next row, and one column to the left and one column to the right, set each of those spaces equal to the beam. Otherwise, we have no split. So we'll just say else data in the next row in the same column is then equal to the beam. And then of course for the next go of our loop, we want to increment the row by 1, and then at the very end we can just return the number of splits. So I'll go ahead and give this a run on our test data, and it gives us 21 just like we expect. So now using my actual input, we get 1499, and testing that out here, fantastic, we get our first star. So let's take a look at part 2. And if we read through part 2, we can see it's actually a quantum tachyon manifold. And if anyone doesn't know, quantum just means it can have multiple states. We're not really sure. So now it's asking how many possible paths can the tachyon beam go. So it could either go all left, or it could go all right, or it could go left, then right, then left, then right. Basically, how many combinations total are there? So what this problem is it's really a depth first search to see how many ways there are to get to the end. So I'm going to solve this using a recursive depth first search function. So taking a look at the code here, first let's write a new function, and we'll call this function solve, and it's going to be recursive. So what is this function going to do? We will use a depth first search, and we will always pass in the data, the row that we're checking, and the column of the beam. So in the last example, or the last problem, there were many beams in one row, but in this case there should only be one beam per row. And if we take a look at the input from before, well, there's going to be many repeated cases, because sometimes it might split into the same box that one has already split into. So my guess is that with an input this big, there's going to be so many repeated cases that if we try and compute them every time, it's going to be too many and take too long. So I'm actually going to use memoization to basically save everything that we've already solved so that we don't have to repeat it. And I'll get to that in a second. So what should this problem take? I'm going to give it a current state, and that should be a list representing the exact state that we're on. And one approach that we could do to solve this is, since it's a recursive function, we could just only take the data from the line that we're on downwards, but I want to save the exact line that we're on. So I'm going to pass in the whole list every time. And then we'll take the line that we are on, which should be an int, and we'll also take the position of the beam as an int, and we will return an int to represent the number of ways that come after this position. So let's take a look, and for now I'll skip the case if it's already solved. And we want to take a look at our base case, which will be when the bottom is reached. And then in our recursive case, we will have to deal with if there's a split or if there's no split. So starting off with the base case, because it's the easiest, we've reached the base case when we have reached this line here, because there's nothing to do after. And so this line is the length of the state, or the length of data, minus 2. So we'll just say if the line that we're on is equal to the length of the state minus 2, then we can go ahead and return 1, because we have found one of the solutions. And then if we take a look at the recursive case, I think we may be typing this a lot of times, so I'll just say that the next line is equal to line plus 1. And sorry, for clarity here, I went ahead and renamed our line variable to just curline, just so that we know. Okay, so let's go ahead and take a look at the split case. So in this case, if the state of our next line and the place that the beam is in is equal to a splitter, then we basically need to make two new states. And we are going to do that by making two copies of this list. However, if we just did, for example, next state 1 and next state 2 are equal to state and state, that's kind of an issue because lists are mutable and these end up just pointing to the same list. And if we try and change anything in state 1, it'll also change it in state 2. But what we want is we want unique copies that do not affect each other. So we're actually going to utilize a Python library here. I'm going to import the copy library so that we can make deep copies, which will make them completely separate copies from each other. So I'm going to say next state 1 is equal to deep copy of state, and next state 2 is also equal to deep copy of state. So that way they're completely separate. So now we can just go ahead and insert the beam into the next states. Okay, and I just said next state 1, next line, and one position to the left of our current beam, one position to the right of the current beam is equal to the beam. And if we were writing just a normal recursive function, at this point we would return our recursive function call, but I actually want to save what this returns and save it into mem. So instead of returning here, we'll just say our answer is equal to solve of, this case, state 1 and our next line and beam minus 1, because remember we want to pass in the column that the beam is in. And we can go ahead and add that to the result of that, the same thing for next state 2. Remembering here for beam to go 1 to the right of our current beam position. And that should take care of the splitting case. So now let's take a look at the no split case, which we'll just say else, and this one's easy. We'll say state, the same state of the next line, and the same column that the beam is already in is equal to another beam. And this time our answer is equal to just solve of state, next line, and beam. So now we have our answer of basically how many combinations come after the state that we're current in. And so let's go ahead and say mem, and for our key we need a unique identifier for each state, and we can identify that state by our current line and the position of the beam. So if we ever come across where this current line and where this beam is again, we know that it'll always be the same every time. And so we'll just go ahead and set that to answer. And then finally we can return the answer here. So the last step of this is to actually utilize the values that we've saved. So finally, at the very top, if it's already been solved, we can say if current line and beam are in mem, then we can just return mem of current line and beam. So I think this should be good. So now let's just go ahead by finishing up the actual solution for part 2. And we'll say data is equal to parse data to get that list in with the beam already inserted just like before. And we want to go ahead and find the initial position of the beam. So say find the beam for column in range, length, data, and 1. And if data 1 and column is equal to the beam, then we can just say beam is equal to column and break. So then we can just return solve of data, and we want to skip the line that the S is on, just go straight to the line that the beam is on. So we'll take everything after the first line, and then we know we're starting on line 0 since that's where the first beam is, and we want to start checking at the beam that we found. So if we go ahead and give this a run now, may take a little bit of time. And actually, let's go ahead and fix this here. Of course, not state, but current state, which I'll also fix here down in the copy function. And I'll also fix that here in the no split, and also in our answer, geez. And one more right here. So now if we go ahead and run again. Okay, so that took about 20 seconds for it to run. So with it already taking that long, it's a good thing that we made the mem. And it may vary depending on your hardware. So just be patient and let's go ahead and test this out. Okay, and testing this out here. Fantastic. First try. So thank you for watching. This has been Advent of Code Day 7 in Python. And I'll see you back here again tomorrow. Thanks.